Daniel says alive and well. I suppose that's better than either option. Dead or not well, I suppose. Right, I have the second cup of coffee of the day, so I'll be hyper by the end. Oh, Brian got his COVID vaccine. Any side effects so far? Oh, 30 minutes. You'll probably be fine. My arm was sore for a week after, but it always is, no matter what they do to me. So, let's see, where were we? So we, actually, let's just take a quick look at what we did, just to make sure that we're on the same page. Yeah, so we did that, okay. And we filled in the table. We need to write down exactly how to fill in the table. And what I want to do is, I just want to write down what a configuration is, and basically a configuration of a parser is just one line of these with all the states removed. Actually, let's take a copy of this. See if I can do that without screwing it up too badly. We'll copy that, and then we're going to paste it here. And then I'm going to try to delete some stuff in here. I'm going to delete that. Actually, we'll get rid of that as well. Get rid of that. Get rid of this, 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 this. This could be dangerous. That, 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 this, 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 that, 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 this, that, 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 this, this. And I'll just get rid of these red lines. Now, if I then take, I wonder if there's a way to do this. If I take this, can I change the color on that? I can. I will make them all red. And I think I'm going to delete this, $$ thing here as well, because that's just to signify end of file. There we go. And now I'm going to take this and move it there. This and move it there. This and move it there. This goes to here. That goes to there. That goes to here. This to here. This to here. And this to here. Does anybody recognize that that sequence of sentential forms, right? So what we have here is we have a sequence of sentential forms. And there's one thing I do want to do before we go any further, and that is to note that these two basically look the same. These three basically look the same. And those two basically look the same. It's the derivation in reverse. It's the derivation, it's the meaning. Yes, it is recording. Yeah, I've been recording from the very beginning. There it is. Look, no, that's not. This is not the right red dot. The red dot is because this is the QuickTime red dot, and we're not recording through QuickTime. We're recording through WebEx, and yes, it is recording, so it's good. So it is exactly the derivation in reverse. Actually, it's the rightmost derivation in reverse, isn't it? Now, why are there these green boxes that represent the same sentential form but show up a number of times? Anybody who can, the coloring should sort of give that away to a certain degree, right? Anybody want to take a stab at that? Yeah, so it's when I take input away from, well, I take something away from the input and put it onto the stack, right? That really just means, look, that was on the input, now it's on the stack. That was on the input, now it's on the stack. That was on the input, now it's on the stack. And then, of course, we change sentential form when we do the reduction, which is when the handle is on top of the stack, right? So removing state numbers and combining stack and remaining input for each step or configuration results in the reverse rightmost derivation of the input. So we could define a configuration of an SLR1 parser as a pair where this is the input remaining and this is the stack laid down. So it's laid down sort of that way. And initially we have this, and then that's input. So here's my stack. Here's my input. So the equivalent configuration looks like $0 A1 ... AN dollar. Now we can see that if I take, let's just make a copy of that. Copy, paste. So if I take that and I get rid of this thing here, I get rid of this thing, we'll throw away those things out there, and that's just the string, right? And by the time we're done, we have no more input, and we should be in the accepting state with the start symbol on top of the stack. That's exactly what happened here, right? We started with just the input, and then we went from this configuration, or from this sentential form, to this one, 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 and to this one. And we can see that if we do a rightmost derivation, then we develop this one first. We get that. Now we develop this to be this. That E becomes F becomes ID, and then that E becomes F becomes ID. So it actually worked. And I'm not saying that as I'm surprised, because that's how it is. Now, if we can represent the stack and the input as a configuration. Then we could also ask, what does shift and reduce do to configuration? So let's start with, I don't know, $0x1 S1 x2 S2 dot 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 xm sm, and some input which is x little x, that's little xi, so these are big x's, little xi plus 1 dot 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 x in dollar. And now let's say that we have shift S. So what does that do to this? Well, it takes this guy and moves onto the other side of that separating comma, and then pushes the state S on. So that's easy enough. So we get $0 x1 S1 dot 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 xm sm little xi s, and then little xi is gone from here. So we get that. So that's easy enough. What's the next one? We got reduce by. So we just say A goes to alpha. Now, in order for us to do this, we need to know how long alpha is. So let's assume that the length of alpha is r, because that's the length of the handle. And we got to remove r symbols and r states. And then we got to put an A on the stack. And then we have to put whatever's in the go-to table on top. So if I do this, then we get $0 x1 s1 dot 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 all the way up to x m minus r sm minus r. And that sm minus r, that's the one that tells you what state were we in when we had that particular item where the dot was all the way to the left for that guy there. Then we get an A, and then we get S, and we didn't consume any input, so that's the same. But S is equal to the go-to table on an A, oh, the other way around, isn't it? In state S m minus r, comma A. And that's it. Yeah, I think that's it for that. So not too bad. Any questions so far? Are we good? Right. So let's see what we can do here. So we'll have a state I sub j, and we're going to put some stuff in here and just see what we can have. Now I can have in here, we can have completed items. They look something like that. So dot all the way to the right. And what sort of stuff happens when I have a completed item? Well, then I have reductions. So this gives me reductions by A goes to alpha beta in the action table for row J, that one, and all the columns for elements in follow of A. We remember we talked we could just, we decided not to just fill up with reductions, so we were going to use the follow set, because then at least we never, well, that's not true, then we're less likely to get ourselves into a configuration that represents a sentential form that couldn't appear in a derivation of the input string. It can happen, and we'll see when we get to LR1 why that is. Right? So that was that. Now, what could we also have in there? We could have non-complete items. And we can really kind of have two different kinds, right? We have the ones with, so let's just say let's use something else. Let's say B goes to beta dot A gamma. So dot in front of a terminal. And we could have, I don't know, C goes to gamma dot X delta, where the dot in front of a non-terminal. Okay, well, if the dot is in front of a terminal, then this gives us a, well, actually, what we get is so we get something like that, and shall we call that IK. So we get an arrow pointing to a new state, and that's the state that we're going to shift to. So we'll make this a that's a shift of A onto the stack and move to state K, which is that one. Now, similarly, I can have one with an X on. Shall we call that one IM? So that's a entry into the go-to table for row J and symbol X. So we can summarize. Let's see, how should we do this? If state ij has A goes to alpha, then the action table at state j, comma little a, is reduced by A goes to alpha beta for all A in the follow set of capital A if state ij has a goes to, what did we call that? No, that was a b. B goes to beta dot a gamma. Then action of j comma little a is shift s, where s is where is the state where the arrow with a points to when leaving state ij. So that state. And if state ij has c goes to gamma dot x delta, then go to j comma x is y, where y is state to which the arrow marked x leaving ij points. Well, there we go. And if you go and look at algorithm 16, that is exactly that algorithm. Right. So there we go. What do you think? Easy enough? Yes, no? All right, we'll do something else then. Yeah, seems clear. It's not bad. Now, what can go wrong when we do this? So let's just look at so if action of some state comma some symbol has multiple entries, then we have a problem. Now, these entries can be shifts and they can be reducers. So let's see, possible combinations. Can I have can I ever have a problem that exhibits a shift conflict? Now, what would that mean? Well, it would mean that you can shift two different places on the same terminal. So for that to happen, I would have to have a state, call it ij, in which I have something that might look like this. But that's not a problem, right? Because what I do here, we just say, all right, fine, on an x, we go to this other state in which we have a goes to alpha x dot beta, and b goes to delta x gamma. And then we apply the closure operation, and that's it, right? So this is never a problem. So there's no such thing as shift-shift conflicts, because that was one of the things when we compute the go-to set of ij on an x is that we gather everything with the dot in front of the x, put it into the new state, move the dot one over, apply the closure operation. So no problem. Never. What's the shift-reduce conflict? Let's see. So what if I had something that looked like this? Again, we'll call it ij. I need to create something that I can shift on. We can use that one we had before. So that one, for example. And then I need something to reduce on. I don't know, b goes to delta dot. So clearly there's going to be an arrow leaving here on an x that takes me over to a goes to alpha x dot beta. There might be some more stuff in here, but it definitely looks like this. What has to be true for me to have a problem here? Well, if I ever wanted to reduce that b goes to delta guy in column X, then I would have a problem because there's definitely a shift in column X, row J. So the question is, when do I want to reduce for X? What would have to be true for X to be one of the symbols that I'm going to reduce on? If follow of B contains X, then there is a problem. Very much so. So yeah, well done. So if X is in the follow of B, because look, that's what it says right there, right? We have a completed item, and we're going to reduce by everything in the follow of A there. So that's exactly the right. Follow of B there is a problem. So if X is in follow of B, then we have a shift reduce conflict. All right, what about reduce? Let's see what we can do there. Oh, let's make a state. So what if I have something like that? Well, we know that action j comma little a is reduce by a goes to alpha for all a in follow of a, and action that is reduced by b goes to alpha for all a in follow of b. There you go. So when do we have a problem here? Well, we have a problem if there exists a terminal for which I should do a reduction by both of the rules at the same time. And that's the problem, right? Because either that handle alpha becomes an A or it becomes a B. It can't become sort of a Schrodinger left-hand side. So what would cause that to happen? Anybody? Well, the two rules would be the same. That never happens, right? Because if they were the same, then remember these are item sets, so sets are not multisets. So if A was equal to B, there would only be one of them. But is it possible to get this and that to happen for the same A? So are there some A's for which I get two entries? Little A's. if follow of A and follow of B are not disjoint. Yes, indeed, very much so. So let's write that down. So if little x is in follow of A intersected with follow of B, then we get a reduce conflict on X. That was also an X up there, right? So how do I fix that? Well, you go and sort out your grammar, because or you could choose to say, yeah, I'm going to be greedy and I'm always going to favor shifting over reducing. So that way I'm going to end up eating more input. So you can sort of resolve shift reduce conflicts by saying, yeah, I'm just not going to reduce, so I'm just going to take the reduce actions out of there, and then now you're just left with a shift, and that's just what you're going to do. Now, how do you reduce, not how do you reduce, how do you solve a reduce problem? Well, there's unfortunately no easy way to do that. And if you get reduce problems, it's probably because your grammar is in a bad shape. So you need to sort of sort out your grammar. And you can probably see now what happens if when you type in a grammar like you did in cup in phase 1. If you forget one of the or symbols, then all of a sudden, all hell breaks loose, because now you have a different grammar, and you get all these shift reduce conflicts, and you can see how that could possibly happen when you type in the grammar incorrectly. Right. So now let me ask you something else. No, it was not and, that was of. If we go back to here, which is where we were last time, I just find a bigger picture, and I find this one here, right? Can I take a picture of this entire thing? Probably if I go there and I say, okay, that didn't seem to work. Select that one, copy, done. Done. Close, go back here, and I say, oh, paste. All right, so let's just go take a look at this one. Let me clean it up a little bit. Oops, that's not clean up. That's much worse. What can we do? Yeah, we can take that out. I'm going to take this out. I'm going to take this out. That. Ah. What the hell is happening? Down there. And then I want to get rid of that. Alright, over here I want to get rid of that and that. And that. Up here. That. That and that. And that. Down here. That. Up there. That and that. This might have been faster to just clean up yourself by hand. There we go. That one, that one, that one, that one. All of this. All of that. That one. That one. That one. Over there. That. That. Over there. This. That. this. That here. That here. All right, I think we have a nice graph, right? So I want to just add a little bit to it now that I've taken something away, because I want to say, what is this? Well, that is the go-to of I0 on an E, which is the closure of the set that consists of S goes to E dot and E goes to E dot plus F. And what about this guy here? I4. Well, that's the go-to of, I don't know, I0 on an open bracket, which is the closure of F goes to dot E. Let me just highlight that. And I'll highlight that as well. And I'm going to highlight that. So you could go through and you could do all the other ones if you wanted to as well. Now, this one first here. This one is by definition. That's how we define this thing. We said, how far can we get without having done anything? That's the definition of what I0 is. And then the rest of them simply followed by the construction of using the epsilon closure operation from NFA to DFA, from the NFA to DFA algorithm. And then we just define these go-tos as being, gather everything with a dot in front of whatever's on the arrow, move the dot over, and apply the closure operation. And we can see that when we apply the closure operation here, we ended up getting all of these guys. When I applied the closure operation here, I got nothing. And when I applied the closure operation over here, I got all of those. So if I look at this, and we are going to, I suggest that we're going to play a game. And the game is that we're going to take turns removing one item from this graph. Who wants to play with me? One item at a time, under the rule that the set can be recomputed. The set from which you removed an item can be recomputed by applying the closure operation to the remaining items. Once we get to a point where there are no more items that can be removed, whoever's turn it is lose. So who wants to play? You can't win $1 million. Come on, anybody. There's got to be somebody who's still awake. Nobody wants to play with me? We can play for an A. See if that wakes somebody up. So if we were playing for an A, would you want to go first? Or do you want me to go first? Rules are we get to remove one item, taking turns, and whoever is left unable to remove an item, because doing so would not regenerate the graph by applying closure operations, loses. So if we were playing for an A, would you want to go first, or would you want me to go first? Sounds like the game is fixed. Well, all games are fixed to a certain degree, and this is Vegas after all. So the house always wins. But you actually have a chance to win here, because you're being asked to set the rules, right? So the game might be fixed, but you can impact the way that it's fixed. So let me just think for a second here. Hold on, I can't count. All right, anybody got the answer? Uh, will the person that goes first win or lose? We can sit all day and stare at each other. There's got to be 1 out of 49 people who dares to take a guess, or at least dares to play, and maybe tell me what the rules are. I'll take a stab. All right. So there's Janelle and there is Louis. What say you both? Would you like to go first, or would you like to go second, aiming for a win? Oh, you want to go first? Benjamin thinks it's a lose. But so when you say it's a lose, do you mean if you go first or if you go second? If you go first, you lose. So Benjamin says if you go first, you lose this game, and Janelle says if you go first, you win. Inconceivable. Never get involved in a land war in Asia. That's I love that movie. Look over there. What's that? Right. So here's I never go into Sicily when death is on the line. So in order to figure this out, um, I think there's an odd number. So first means win. Well, there's an odd number of. So let's see. Matthew says the person who can't remove an item that isn't regenerated by closure loses. Yes, right. So if we can look at this, we can figure out how many of the items are in all of these sets that were added to those sets because they were added by the closure operation. Then we should be able to figure out if there's an even number, then whoever goes first wins, and if there's an odd number, then whoever goes second wins. And the easiest way to do this is to ask the question, what do all items that have been added by the closure operation have in common? Well, we could go back and look at the definition of the closure operation, which is here. And that closure operation says blah 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 blah. Then add that. So what do all of these added items from the closure operation have in common? They start with the dot all the way to the left. Aha! Right? So now I go back to here and I ask the same question. Would you like to go first or would you like to go second for a win? So an even number of items added by the closure operation is a win, and an odd number is a lose. So Janelle still wants to go first now, or wants to go first now. And now James wants to go second. Okay, it's turned into complete pandemonium. We could probably do this. We could probably do this on TV. I wonder if we can get syndicated late at night. Louis says I count 11 dots, so he wants to go second. And see, this is how I make my money. And Benjamin is now up to 5% confidence on that. Shizao says no, odd means first win. No, an even number of items added by the closure operation means that going first is a win. The first second argument isn't really compiler related. No, but I'm trying to get you to see something here, and this is a way to try to get you to see it so that you won't forget it, because then when you look at this again, you'll remember this stupid game show that we played. It's called pedagogy, and that's something you learn when you get as old as me. So if I say that if it's odd, then by going first, you remove the last, and the person going second doesn't have one to move. So you want to play? I'm going to go. Do you want to go first? Or want to go last? If you're sure you can have a winning strategy. Who wants to? Who wants to take me on? So who? I'm gonna. I'm gonna. Come on, somebody. Somebody. Tell me what they want to do. So yeah, you call. You count. You count 11 Jameses. That's a lot of James. I suppose it depends on how much one James is. But it's a lot. Okay, that's good to know. Well, rather have too much than too little, right? So is there somebody who wants to go second? So I can go first? Then I'm ready to go. I'm just going to change this to red. Right. Damn it, Louis. Right, so Louis says, oh, wait. Added. So 10 have dots to the left. Not counting the original, because that one wasn't added by the closure operation. That one was the foundation for starting all this out. So surely that last one there, or that first one here, this one here, is the odd one out, because that one was not added by the closure operation. So if I remove that one, then we get in trouble. So here's the game. For the win, I go first, I remove this one. Then one of you goes, you remove that one. Then I go first again, and now you go second. I go first, you go second. I go first, you go second. I go first, you go second. Oh, so I lost. So it's the other way around. Oh, whoever goes first loses, right? So if you have an even number, don't go first. Go second. The point is that all of these items with the dot all the way to the left were added by the closure operation. Except this one. So if I, so Matthew says, wait, I thought we were removing items that aren't generated. No, we're removing the ones that are generated by the closure. Sorry if that wasn't clear. So if I remove all those things in red, then I can regenerate the entire graph by simply applying the closure operation over again. So we can say that the kernel of, and I really, but why what? James, I don't understand your question. Oh, for you might want to do that for size, because some of these, when you have a real programming language, get really large. So you would have to use an awful lot of space to save every single one. So if I only store the kernel, then I can always regenerate the entire thing if I need to. And so here we're going to talk about the kernel of, and I'm only going to say item sets in SLR1 states, because otherwise what we're going to talk about isn't entirely true. So kernel of I is a subset J of I, so is a minimal subset such that closure of J, which is the same as the closure of the kernel of I, is just I. And you can probably see how if I took this item set here and I said, hey, I just want a generalized item set. I'm going to erase this one here then. And I have the rest as a generalized item set. Now, of course, I can't say, oh yeah, well, everything with the dot all the way to the left can be removed, because these can't be removed, because these are not generated by any closure operation. So we got to be a little careful by saying that all non-kernel elements have a dot all the way there, except for this guy. But that is true if we're looking at just states from these graphs. So I'm happy with the characterization of non-kernel items being the ones that have a dot all the way to the left, except for this little guy here, because that one was used as the generating set there. Okay. Now, we're just sort of cleaning up a few little loose ends here. Let me ask you a little bit about, or let's look at left recursion. Left recursion was bad for LL parsing. Is left recursion bad for SLR parsing? Well, I don't know. Let's find out. So we can do example 431, which is very simple. And we can fairly easily figure out whether or not this is going to work, because we can just say I0 is the closure of the set that consists of S goes to dot A. Okay, so we get S goes to dot A goes to dot A, little a goes to dot B, right? On a capital A, we can go here, we get S goes to A dot, and we get A goes to A dot A. And at this point, when we've created this state, we gotta take a quick look at that and say, oh, that could be a, well, what kind of conflict could there be in this state I1, if any at all? There could be a shift reduce. When would there be a shift reduce conflict? Can you tell me that as well? If A is in the follow of S? Yes, correct. Is A in the follow of S? If S is the start symbol? Nope. What's in the follow of S if S is the start symbol? Dollar. Right? Yes. So you see how this just works. So we're good. There's nothing bad there. Right? What can we do from here? We can go and do an A, which gets us to A goes to A dot. Or we can do a B from here, and we get to A goes to B dot. And then I can ask you, are there any states with conflicts in this thing? We ruled out any conflicts here. There's just one state or one item here, and there's just one item here, so there couldn't be any conflicts. Are there any conflicts here? No, because that was just that original closure application of that particular start symbol or start item. So we're good. There are no issues. Although, what would happen? It's replaced by A goes to epsilon. Would that be a problem? Well, let's see. We would get that one would be deleted, and that would be just A goes to dot that. And that's going to call for a reduction in the follow set of A. And what's the follow set of A? That's $a. That's fine, because I can only get out of here on on a capital A. So yeah, that would probably be fine as well. Here's one I want to try. I've never tried this one. Let's do this together. What about that one there? Have you ever seen this grammar before? So it's a palindrome over just one. It's a weird ass palindrome, if you ask me, because it's just a bunch of A's, right? There are no B's or anything else. It's just A's. Is this going to work? I don't know. Let's give it a go. I0. I'm not going to write down the closure thing or whatever. Oh, we need S goes to A. Otherwise, we can't do much. Well, at least we didn't have any problems there. Okay. And the little a gets me to here. That's a goes to a dot a. And then we get a goes to dot a. And a goes to that. Around there on a little a, over here on an a goes to a dot a. That doesn't change anything when I apply the closure. Then the final a. This is very Canadian. So we get that. Does that work? Let's see. Any conflicts here? No. Any conflicts here? No, no. There? Well, let's see. If little a is in the follow of capital A, then we have a shift reduce conflict. And I suppose we can actually say the exact same thing there. So what is the follow? What is the follow of A? So the follow of A is little a union follow of S. So we get a little a dollar. So therefore, shift reduce conflict on A. And if you think about it, how on earth is it possible to determine when to do the epsilon reduction? So in other words, when do I know that I have the two middle A's on top of the stack? I cannot know that without counting the length of the entire input and figuring out where it is. So this grammar is not LL1, it's not SLR1 either. It turns out that it's not LR1 or LALR1 either. This thing is just not parsable at all. Could I tweak this thing to make it LR SLR1? You literally need as many look-aheads as the length of the string, right? Well, you definitely need to know how long the string is. So you need to be able to, yes, right, yes. So you need to be able to detect where's the end of file. So you need a complete variable number of lookups depending on how long the string is, look ahead. So that's going to be a mess, isn't it? So what happened if I what is it in this grammar that's causing my trouble? It's the epsilon, isn't it? Because that epsilon in the middle of the first half of the string and the second half is really not very. You really can't see it, right? That's the problem. So at some point, you have to do the reduction here or here, which makes that A sort of appear out of nowhere because we do epsilon becomes A, and then that's going to be the A with this coming from the remaining input and that being on top of the stack before the A goes on. Now, what would happen if I did, so if I said, all right, I'm going to do B instead there. Well, then I would get a B here, and I would get A goes to B here. So now this reduction happens in a completely different state. Similarly over here, I get a B there. And the reduction happens in a completely different state. So now I don't have the shift reduce conflicts anymore, and Bob's your uncle. Because keep shifting A's until you see the B. When you see the B, then you can shift one more A, and then you can now do A, capital A, little a, and you continue on. So it's sort of you spool up, and then you can unravel it afterwards. So it was that epsilon there that becomes a problem. Right, one more. What about so an LL parser cannot handle left recursion, but an LR parser can. Right off the bat, can an LR or an SLR parser handle right recursion then? Or are we going to be in trouble with that? Because right recursion was fine for the LL parser, right? That's how we sorted out left recursion. We turned it into right recursion. So what do we think? Do we think that that this could potentially be a problem? No, both of you say no. Well, let's give it a go. We can just use this very simple one like we have before. And we've done a million of these now, so we're on autopilot. S goes to dot A, apply closure, A goes to little a goes to little b, that's it. Out of here on a capital A to I1, S goes to A dot, that's it there, no problems in that state. Little a out here, capital A, little a dot A, apply closure, A goes to dot A goes to dot B. Any problems here? No, we don't have any complete items, so that's not a problem. B goes to there, A goes to B dot. No issues there. Over there on a B, around here on an A, and out this way on a capital A to A goes to A dot. Voila. Let's see. No problems, no problems, no problems, no problems, no problems. This is fine. Completely fine. So that's good. That's good. So it seems that we're doing good with this stuff here. So now let's go back. I have one more. So let's do the dangling else. That's part 2. Right, so we had S goes to that statement if expression, then statement prime, or O for other. And S prime is else statement or epsilon, and other is something. So let's see. Let's try. I0, and here we'll just have statement. Statement is if E S S prime and S goes to dot O. Now we can go this way on an O. So that's all the other ones. So there may be less interesting, depending on what they are. As long as they don't start with an if, then it certainly isn't a problem. Which means that we can go down. Ooh, I just found. Oh, that's fine. If, so we get S goes to if dot E S prime. And now there might be some stuff with E which really isn't all that interesting for what we're doing here. So let's just say that we've done an E. We get to S goes to if E dot S prime. And of course now we have a dot in front of an S, so we compute the closure and we get all the stuff from I0 again. S goes to dot if E S prime. S goes to dot O. Well, we should be able to go there on an O, and we should be able to go there on an if. And if we do an S, we get to go to S goes to if E S dot S prime. And S prime is epsilon or dot else S. All right. And finally, else I get S goes to if E S prime dot. Right, so we got sort of part of it right there. You've seen a good 10 of these by now. And actually, we can't really talk about this if I don't give them numbers. So with your expertise eyes, and you sort of just do a quick look on this one, are there any states that pop out as potentially being problematic? And are there some that are obviously not an issue? So should we do the ones that are not an issue? And I'll just sort of green check them. Are there any issues in I0? Under the assumption that I say O doesn't go to anything that sort of starts with an if. So those also your whiles and your do's and your fors and what have we not. So I mean, we could believe in Benjamin's God says no for this as well. Oh, he says it looks fine. So that one, proof by Benjamin. What about II? Sorry, I1. Well, there's not there's just one thing there, so that's good as well. This one, no problem because there really is just one thing. There are no reductions down here, and we can't have shift conflicts. So there we go. So that leaves us to just this one here. I was going to draw a face with shifty eyes, but I don't know how to do that. Are there any problems in there? And if there are any problems, what are they and how do they exhibit themselves? There's only one reduction item, so we don't have reduce conflicts. We could potentially have a shift reduce conflicts, and we might have a shift reduce conflict if what? Well, we're only shifting out on one thing, right? That's else. So that's going to be if else is in whatever I causes S prime goes to epsilon to reduce. So that's going to be the follow set of S prime. Now, what on earth is the follow set of S prime? It's the follow set of S union some more stuff. All right, what's the follow set of S? Well, it definitely. So actually, let me write this slightly differently. Let's say that that is including what's included in the follow set of S. Well, it's the first of S prime minus epsilon because we're not allowed to put epsilons in follow sets, right? What's the first set of S prime? I don't know, but it's definitely it definitely has an else in, doesn't it? So if else is in the follow set of S prime, then we're in trouble. Else is in the follow set of S prime, so therefore we have a shift reduce conflict in that state. All right, so dangling else, still a problem, still not solved. Now, the way that we would attempt this in an LR1 would give us exactly the same problem. So there's no point in doing that either. The problem is that that grammar is just flawed. So we have to rewrite it in a completely different way, which seems like magic, and I'll grant you that. I don't think I would have come up with this solution myself if I hadn't seen it done in many grammars. And you can look on page 222 to see a snippet of how it's done. It basically boils down the Java or the Espresso grammar that you already implemented. Right. So that's the end of today. What we have to do next time, I want to do example 433, and then I want to talk about the problem with that, and then I want to do LR1 parsing, and then that's it for parsing. We're done. We're moving on um, to something else, which is, I guess, we're on to chapter 7, which is type checking. And you've just started type checking. Oh, should I ask? Are there any phase 4 questions right before we run off? Just remember, not all the types you need you can find in the parser tree. Sometimes you have to make a type. So, for example, if you need a class type for a certain class declaration, then you can make a class type because the class type is just a new class type with whatever it takes in the constructor, which I think is just a class name, isn't it? If you make a class type that has a myDecl or something that points to the actual declaration, remember to set it because you might need it later. But I think that's all she wrote for today, and we're down to 45 people. That means half of the class is showing up. Shouldn't I5 contain S goes to else dot S? Shouldn't I5 contain that? Oh, yes, it should. Should it? Oh, well, yeah, duh. Yeah, this is completely wrong, right? Well spotted. I'll quickly fix that. It should say or maybe not quite that thick. Else dot s. Yeah, there you go. One person paying attention, keeping me honest. Good job. Anything else? If not, then what are we today? Thursday? Is it really Thursday today? It is Thursday. That week just went flying by. That means I won't see you tomorrow. Any of you. So Monday office hours, I guess, or Tuesday, if you can make it. So have a good weekend and see you next week. No messing around. Go do your type checker. All right, we're done. Bye.